Now before we start with this question, what I've done is I've basically copied the diagram that we're given. We're going to need to add some more information on this. So let's just go through it. We've got this uniform rod AB of mass 4 kilograms and it's of length 1.4 meters. Well, first of all, if it's a uniform rod, the weight must act in the middle. So we'll just put that there. And if we mark that in, it had a mass of 4 kilograms, so the weight is going to be mg, 4g newtons. So we've got that force on there. We're told that the end A is resting on rough horizontal ground, and we've got a light string here attached at B and to C, and it's perpendicular to the rod. So we're also told then that the rod is in equilibrium, and we've got to find the tension in this string here, BC. So we need to mark on some more forces. First of all, there's that tension at B. It's going to act perpendicular to the rod. Let's just call it T newtons there. And we've also got the fact that it's in contact here with this rough ground. So there's going to be a normal reaction. Let's just call that R newtons. And there'll also be a force to the right, preventing it from wanting to slide to the left. So we'll mark that in there. Let's just say it is X newtons. Okay, well, if we're to find this tension T newtons here, we don't seem to know too much about R and X. So this is a typical question where if we were to take moments about A, because these forces pass through A, they're not going to enter the equation. So we're just going to have an equation with the weight and the tension in, if we take the moments then about A. So that's our starting point. We'll take moments about A, let's just put that up here, and we've got to take a positive sense. And it doesn't matter which way you go, whether it's anti-clockwise or clockwise, but I'm going to choose anti-clockwise as positive. And the reason for that is that it just keeps T positive in my equation. But that's totally up to you. So if we take moments, remember it's going to be the force times the distance back to A. And if we start with T is going to want to turn AB in an anti-clockwise sense, in the positive sense. So it's going to be T multiplied by the distance 1.4. Okay, so we've got that one. Now if we take the weight here, I'm going to put a dotted line in here, perpendicular to the rod, and we'll put one as well down in this direction. Okay, now that means that the angle 20 degrees shows up in here, 20 degrees, just mark that in. So as for the weight, we can split this into two components, one perpendicular to the rod and one down the rod through the point A. Now the one down the rod through A is not going to have any effect in turning it about A. The one here, this perpendicular component, it's going to want to turn it in a clockwise sense about A. So that's in the opposite sense to this, so it must be minus. Let's just mark that in as minus. And this force acting perpendicular to AB is going to be 4g cos 20. So you've got the force 4g cos of 20 degrees, and that has to be multiplied by the distance from here to A. Well, being a uniform rod, it's going to be half of the 1.4 meters, so it's going to be 0.7 meters. So we'll just put that in as 0.7. So this is the resultant moment of the rod about A. But we know it's in equilibrium, so that resultant moment should equal 0. Okay, so it's just a simple case of rearranging this equation for T, and we'll take G as 9.8. So therefore, if we add this term to both sides and divide by 1.4, we're going to get that T equals 4G, 4 times 9.8 then, times the cosine of 20 degrees, and that is multiplied by 0.7. So that would in theory give us 1.4t, but I'm going to divide at the same time by 1.4, and that gives us t. And if you pass this through your calculator, you'll find you get 18.41797 and so on. And if we round this, say, to 3 significant figures, that tension is going to be 18.4 newtons to 3 significant figures, 3SF. Okay, so I hope it's given you an idea then how we can get that tension T.